Okay, let's take a look at some rules for probability models. Anytime I set up a probability model, it must satisfy these rules. If it doesn't satisfy these rules, it's not a probability model. Let's go through these rules and see what they say. First rule says the probability of the whole sample space is 1. If I play a game, say of rolling a die, what's the probability of observing the numbers 1 through 6? That's 1. If I roll a die, I'm going to observe one of those numbers. So the probability of the whole space is 1. Now what do we mean by this symbol here? This symbol is shorthand notation for curly brackets with nothing inside. What is the probability of nothing happening? 0. If I roll a die, I have to observe something. This statement here is put in mostly for logical completeness, but all these bracket notations, we can think of a bracket as kind of indicating the boundary of a box, and what's inside the box is between the two brackets. Here I don't have anything in the box, it's an empty box. What is the probability of observing nothing in the game? 0. For any event, A, it doesn't matter what it is, if it's going to be a valid probability model, the probability must be between 0 and 1. Could be 0, could be 1, it can never be bigger than 1, and it can never be negative. If you come up with a negative probability, it is wrong. Cannot be a valid probability model. Now, the next rule says the following. The probability of the complement of an event is equal to 1 minus the probability of an event. Let me illustrate that using a Venn diagram. Venn diagram uses a rectangle to represent, if you will, it's kind of like our box idea. And what's inside are the things I can observe. Let's call the things inside here A. So this is the sample space. A is an event in S, which consists of some portion of S. Everything outside of A is what we call a complement. So if, in this example, let's use the letter H to represent the outcomes 1, 4, and 6 in the rolling of a die, what is the complement of H? Well, it would be a 2, a 3, and a 5. This is kind of a visual representation here. The probability of the complement is 1 minus the probability of the event itself. In a way, it's just like a bookkeeping rule. Now, let's talk about the word or. Let's see. I think I'm going to go back to this here. And there is an event called R or G, and what it is composed of would be the outcomes that are found in G or should be either in R or in G. Now in this case, that would consist of 1, 2. I'm getting those two from R, all right, and then a 3 that's coming from my G, and then I guess a 4 and a 5. Now let's do R or B. Again, using this notation over here. 4 is found in both. In this case, the event consists of a 1, a 2, a 4, and a 6. I don't put down 2 4s. That doesn't have any meaning in this context. You either get a 4 on the top or you don't. Okay, now, we also use the following notation. This is sometimes written A union G. This looks like a U. It's not really a U, but it looks like a U. And if you had some set theory sometime in your past, you may have talked about unions. If you recall in your college algebra, maybe, you talked about intervals of numbers. Those were sets as well. Intervals of numbers are actually infinite in size. You have an infinite number of values. In this case, the sets are finite size. Okay. And you probably talked about, you may have talked about intersections and unions in your college algebra. It's the same deal here. All right, now, there's a rule I've stated up here that says the following. The probability of A or B. A or B is a new event, as I've described over here, which consists of the outcomes that are found in A or in B or found in both. The probability of that new event is equal to the probability of the first event, A, plus the probability of the second event, B, provided A and B are disjoint. Now here the letters A and B stand for generic events. Now, I stated over here, R and G are disjoint. So this rule would apply. The probability of R or G, which I might also write as the probability of R union G, is in fact equal to the probability of R plus the probability of G. And I figured those out over here. I guess R was 1/2 and G is 1/3. So this is 1/2 plus 1/3, and that's 5/6, which is in fact the same thing I get if I take the number of outcomes here and divide it by 6. This rule here only holds when A and B are disjoint. One way of thinking about that is as follows. Suppose, again, I have a Venn diagram. I have two events, A and B. The probability of A or B, which is the same thing as the event which we call the union of A and B, is simply the probability of A plus the probability of B. Okay. Let's look at this rule here. Here I have the word and. Okay? I'll come down here. I think what we'll do is we use R and B there. R and B. The R consists of the outcomes 1, 2, and 4. B consists of the outcomes 4 and 6. This means outcomes that are found in both. So if I look at R and B up there, the only outcome that's common or found in both would be 4. All right, now, this notation we sometimes use, we'll write R intersection with B. This is, if you will, the other symbol, the union symbol flipped over. It looks like an upside down U. It's not really an upside down U, but it's an intersection. Intersection means something that's common to or found independent. Okay.
You said R and B independent.
Are independent, that's correct. They're independent. Again, there are two ways of thinking about it. One way is it fits this description here. The probability of R and B is equal to the product of their probabilities. That defines it.
They don't have something in common with probably is it?
They cannot be independent. Why is that the case? Well, let's look at, let's see, what was, well, I had a green up here, which consists of a 3 and a 5, and the red here is a 1, 2, and a 4. If this is my green, is the green and the red independent?
Yes.
No.
Why?
Because if I tell you that red has occurred, I know that green has not. Let's go back here. The green consists of 3 and a 5. All right? R and G are not independent. They are, they're not independent. When something is not independent, well, we mean dependent. If I tell you that R has occurred, what do I know about G? I know G has not occurred. See, if R has occurred, that means I had a 1, a 2, or a 4. That means for certain G has not occurred. If I roll a die and I tell you that G has occurred, I know this has not. There is nothing common to both R and G.
So they are independent. Nothing.
They are dependent. They are not independent. Independence is these two, R and B, write that over here. R and B are independent. R and B are independent because if I tell you that R has occurred, you have no more information as to whether or not B has occurred. Or, on the other hand, if I tell you B has occurred, you don't have any more information as to whether or not R has occurred.
But if you tell me R has occurred, you will have information about the G will occur.
Okay, if I know R has occurred, that is, I've observed a 1, a 2, or 4, what do I know about G?
Will occur.
Has not occurred. Do you find any outcomes that are common to both of these?
How come it's G?
I'm sorry?
How come R and G is independent?
R and G are dependent because if I know that this has occurred, I know the other one has not. They are not independent, which could be abbreviated to say they are dependent. If I know that R has occurred, there's no point in betting on G. I know G has not occurred. Okay, in contrast, R and B are independent because if I know that either R or B has occurred, that would not in any way help me estimate whether the other has occurred. In advance, the probability of R is 1/2. In advance, the probability of B is 1/3. If I tell you B has occurred, that is, I roll the die, I'm not telling you which of these you've observed here, the 4 or the 6, but if I tell you that's occurred, what is the probability? If you're a betting person, what would be the probability that we can say that R has occurred? Well, there are only 2 possibilities here, a 4 or 6. So 4 is a part of R, so the probability of an R is still 1/2. 2 events are said to be independent if knowledge of the occurrence of one does not change our knowledge of the occurrence of the other. That translates into this rule here. If you have a situation where this is not true, that is, the probability of A and B is not equal to that, then they are not independent. They are dependent. Let me draw another Venn diagram here. In this example, all right, the events A and B overlap. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B.
project Venn diagram, is that an example of?
It's not an example of either one. Independent. Yeah. I'm sorry. They might be independent, but they may not. So in this case, it gets a little more complicated. The reason I put this down at this point is it's an extension of this rule here. Okay? And it's actually on subsequent overhead. So that the rules up there are sometimes better understood in terms of these Venn diagrams. Okay? Now, if you look at the class website, you will see in the general folder a number of files that I've recently put up there that would be of interest. Let's go through one of these.